that we are done with chapter 1, let's do chapter 2. In chapter 2, we'll discuss alkanes, which are straight chains with some branches, and ring alkanes we call cycloalkanes, and their conformations, of course, and of course their geometric isomers or structural constitution isomers. All right, so we already described what alkanes are. They have all single bonds. There's no double bond, there's no triple bond. This is an example of a cyclic alkane. Where you see the black balls, those are carbons. These grayish, whitish balls, small balls, are hydrogens. So you have carbon and hydrogens only in this structure. This is a hydrocarbon. Okay. All right. So what are hydrocarbons? These are molecules or structures containing only carbon and hydrogens, and they will have a general formula CNHM to get alkanes, all single bonds. Alkenes, there must be a double bond. Alkynes, there must be a triple bond, as you see in these structures below. Also, you'll have rings that are doubly bonded and well resonance stabilized. We call those aromatic rings. The best example is benzene ring, which you must have heard of. So this one is aromatic. We'll discuss that in a future chapter, but the ones we are to describe in the next 2 chapters is the aliphatic ones, which are not aromatic. In other words, they are chains. The aliphatic, they are chains. So you could have alkanes which have carbons, CC sigma bonds, and all carbons are sp3. So for example, here, if I am to draw out the carbon on this, on the left, okay, so it's bonded to a CH3. So you have 4 electron domains, it has to be sp3. Here, this carbon is bonded to 2 hydrogens and a double bond that makes 3 electron domains. Let me draw it up showing the bonds. Okay, so again, this is sp2 because you have 2 single bonds and a double bond. The double bond is 4 electrons, which is counted as 1 domain. You have 1s and 2p's, that accounts for the 3 electron domains. And then here you have a single bond and a triple bond. 2 electron domains gives sp. All right, so for in triple bond, you're gonna have 1 sigma bond, which maybe is the middle one, and then 2 pi bonds on top and below. Here you have 1 sigma and a pi. Here you have 1 sigma and 2 pi's. All right, so this one, aromatic ring, this aromatic ring has pi bonds which are alternating. Double bond, single bond, double bond, single bond, double bond, single bond, single bond. That's what we call conjugation. But like I said, we'll cover much of this in a way later chapter. So let's narrow down to alkanes. Okay, so the babiest alkane is methane. It's a hydrocarbon made of only hydrogens and carbons. It's a hydrocarbon. The black ball, like I said, is the carbon, and then these ones are hydrogens. You see the carbon there is sp3 hybridized. One would expect that the bond angle will be 109.5. Molecular shape, electronic shape will be tetrahedral. Okay, you know, one thing with this class, information builds up. You don't want to forget information from an earlier class session. Okay, so now the general formula for alkanes is CnH2n plus 2, for example, and is taken to be the number of carbons in the structure. So let's say you have 1 carbon. So how many hydrogens will you have? You'll have 2, then where n is, put 1, because you already said you had 1 carbon, and then add 2. So the formula turns out to be C1H4. When you add this up, we don't need to show the 1 subscript, so it's CH4 which happens to be that formula of methane. So if you're looking at an alkane with 2 carbons, then the formula will be C2H2 plus 2. It's gonna happen to be C2H6, and that is the structure of ethane or ethane, a 2-carbon alkane with 6 hydrogens. Remember, carbons must bond to 4 other bonds if it's neutral. Alright, so we explained how you can draw line structures, line angle structures with omitting carbons and hydrogens. You know the carbons are always at the end, and they will be in where there's a corner of the vertex, there's a carbon. Now after that, you have to make sure that there's 4 bonds around them. The hydrogens are implied, they are there, they're just not drawn. Okay, so which means this is a CH2, this is a CH2 to make 4 bonds around that carbon. That's a CH2, and of course this is a CH3. So these are straight chains. Some are simple, some are way branched, but all these will have their own name. We'll name this soon. Now you get to have isomers, constitutional structural isomers of alkanes. You cannot make an isomer of a 2-carbon and a 1-carbon and a 3-carbon alkane. The first time you see isomers is with 4 carbons. For example, if I write the structure of the 4-carbon, the open structure we call it, this will be the open structure, and then line angle will be like that, right? Not showing carbons, not showing hydrogens, but I can chop off this part and replace it with one of the hydrogens on 1 carbon over. So if I replace these 2 guys, I'm gonna end up with this CH3 up there. You know, this is a CH3 right here. And then the hydrogen that was swapped, you know, there are 2 hydrogens here. So if I swap the CH3 with the circled hydrogen, then I'm gonna end up with the CH3 here. So if I would draw without showing hydrogens, I end up with this, which means I started with that and then I made its isomer. Both of them have the general formula C4H10, and these 2 are the only isomers. There's no other isomer you can get, so there are 2 isomers there. So an alkane with 5 carbons will have 3 isomers, alkane with 6 will have 5. If you have an alkane with 30 carbons, good luck drawing all the different structural isomers, which should be 4.1 million. At some point you'll give up, grow old and die. Okay, so I'll discuss about isomerism again when it shows up at the end. Okay, so we need to give names to these organic molecules. We use the IUPAC system to give the names of alkanes and alkenes and alkynes. So it's International Union of Pure and Applied Chemistry, IUPAC, and it's a systematic name that everyone uses nationwide, on Earth at least. I don't know about Mars and Jupiter, but on Earth we use one common system. Hydrocarbons are organic compounds containing of carbon and hydrogens, you know that, and they are divided to alkanes, alkenes, alkynes, and some of them could be aromatic. Alkanes, all single bond, alkenes, at least 1 double bond, alkynes, a triple bond is present. So, but for alkanes, I've given you the general formula. The suffix name will be ANE, implying all sigma bonds. So we usually count the longest carbon chain. If it's making a corner, we just track the longest chain on the structure. So here I can number from either side. We'll do the IUPAC rules shortly. I can number from either side. Either way you go, you have 4 carbons here, which makes bute. Bute standing for 4, N because it's an alkane, all sigma bonds, all single bonds. Here you have 3 carbons, and there's no pi bonds, so it's prop. standing for 3 carbons in the longest chain, so propane. And then here you have 5 carbons, so pent, like pentagon, and then there's all single bond pentane. Okay, so this table just shows you the prefix names according to the number of carbons. So whenever you have 1 carbon, again, it's meth, like methane. 4 is but, like butane. Eth is 2, like in ethane. 6 is hex, like in hexane, the alkane. 10 will be dec, like in decan. For purposes of not complicating things, this is the farthest I want you to know. Dodecane, the 12 carbon structure, to know for this class. You can click this link here, and then you practice the questions that are on there, or read the information, more information about naming alkanes by IUPAC system, but I'll still try to want to go over some more. So this has 8, this one has 8 carbons. So if you go by the formula C8, H2, 8 plus 2, then you're gonna get C8, H, 18 hydrogens. If you count these hydrogens, they're 18. If you don't want to show the hydrogens, you need to draw the line angle structure. Then this is what you will do. Remember, there's a carbon at every end, and then you know the hydrogens are implied. They are not shown for clarity. Okay. So you get constituent isomers by branching, and those branched alkanes can also be named. The main process that you want to follow is, first of all, to find the longest. You need, step number 1 is usually to find the longest parent chain, which is what you have in black. If you go this way and go up, or go this way and go blue, the one in black is longer than either way you go. So the longest parent chain is this part in black. The hydrogens are implied. Like here, there's a hydrogen. I know this one because there's already 3 bonds. There's 1 here to make 4 bonds. There's 2 here to make 4 bonds around that carbon, blah, blah, blah. There's 3 hydrogens here. There's 3 hydrogens there. The hydrogens are there, just not drawn. Okay? So first identify the parent chain, and then once you identify the parent chain, anything that's outside the parent chain will be called substituents. Those will be the substituents, which is what we are trying to explain. Just like a tree, you'll have the stem, and out of the stem, you're going to have branches. So our stem here, in this case, is going to be the longest carbon chain. The substituents will have their own name. So depending on the number of carbons, like here we have CH3. I know there are 3 hydrogens because we already have 1 bond. Carbon needs to have 4 bonds around it. When it's 1 carbon, that goes with meth. We said 1 is meth. But because it's a substituent, instead of saying methane, you replace the A and E with a YL because it's a substituent, so it becomes methyl. Here there's 2 carbons. There's a carbon here with 3 hydrogens. There's a carbon here with 2 hydrogens. You know why there are 2 there. I'll keep on explaining. It's because you already have 2 bonds. So 2 bonds are implied. They must be going to the 2 hydrogens. So the 2 hydrogens must be present there. This becomes ethyl because there's 2 carbons. There's this carbon here and this carbon here in the substituent. Again, the substituent is anything that pops out of the longest chain in the alkane structure. So if you have 1 carbon on the substituent, it's called methyl. If it's 2 carbons, methyl. If it's 3 carbons, propyl. If it's 4 carbons, butyl. If it's 5 carbons on the substituent, is pentyl. If it's 6, it's hexyl, heptyl, octyl, nono, decyl. All right. So if all these groups are popping out of the chain, they will have their they are actually called alkyl groups because they make methyl, ethyl, propyl. If these are popping out, they become substituents and they'll bear their own names, which are listed here. You need to know the name of substituents so that you give the official IUPAC name of the hydrocarbon structure you are given in a quiz. Now, the same substituents can be drawn as line angle. So let's say this was the longest chain, blah blah blah. Let's say this was the parent longest chain, blah blah blah. Parent longest chain, blah blah blah, and so on. That's what the parent means. It just means that these groups are popping out of the longest chain. So you have how many carbons? 1, 2, 3 carbons. Propyl. 1, 2, 3, 4 carbons. That's a butyl substituent. 1, 2, 3, 4, 5. That's a pentyl. If this is the longest, parent chain, then this one becomes. This is called isopropyl because I see there are 3 carbons, but the 3 carbon substituent is symmetrical, like the CH3 on top is reflected on the bottom. So we say iso. Alternatively, it's an isomer of a propyl. You see the propyl has 3 carbons. This has 3 carbons, so it's an isomer, so we call it isopropyl. The I is not italicized. I repeat, the I is not italicized. You're gonna need that while writing your name, the official name of the molecule. So this one has 4 carbons. I see 1 here, 2, 3, 4. I'm not numbering following any rule. I'm just counting. So here the straight chain is a butyl. This also has 4 carbons. I think it also has 9 hydrogens. If you show the hydrogens, this one is 4 carbons, 9 hydrogens. Okay, 4 carbons, 9 hydrogens. So this substituent is an isomer of the butyl, so it's isobutyl. Again, I is not italicized. If you cut here, you will have 1, 2, 3, 4. It's still a butyl, but the parent is on the second carbon, so we call it sec. This sec right here should be in italics. Note down that should be italicized. It's very important. We'll use this rule in naming, so italicized. And then of course the chicken foot, I call it, if it's popping out of the parent chain, the longest parent chain, you still have 4 carbons. There's a carbon here. 1, 2, 3, 4. 4 carbons, just like the butyl, but it looks like a it's tetra. It looks like a chicken foot, so to speak. So we call it tart. This tart should be italicized. Okay, it's not typed well. It should be in italics. I want you to know what's in italics, what's not. ISO, they are not italicized. Sec, tart are italicized. Okay, so those are the common ones that I would want you to know. Don't worry about the neopentyl and isopentyl, isoamyl. Don't worry about those. I want you to know about propyl, butyl, pentyl, isopropyl, isobutyl, sec butyl, italicized sec, tart butyl, italicized tart. Okay, so how do we name compounds? So the first thing you want to know is to find the longest chain, numbering from either side. Okay, but you will want eventually to number from the end. That gives the substituents the lowest number possible. So I'm going to choose the blue pen. So I could start from here. 1, 2, 3, 4, 5, 6. Notice it could be 5, 6, 5, 6. Just choose one of these. So anything that's out is going to be a substituent. I would circle it. So I keep my parent chain. Now out of my parent chain, which is the right way to number, the red or the blue? Again, you have to give the substituents the lowest number possible. The only way to know which one gives you the least number possible is to sum up the positions. So like here in blue, I have a 3, and then I have 2 substituents on 5, so I have a 5, and I'm going to write 5 again. Why? Because the methyl here is on the 5th carbon, right? The methyl here is on the 5th carbon, and then the ethyl is on the 3 carbon. I call this ethyl because there are 2 carbons in there. Ethyl substituent, these 2 are methyls. Okay, CH3. there are 3 hydrogens there. There are 3 hydrogens here to make 4 bonds around the carbon. Okay, so 5 plus 5 plus 3 is 13. I just want to find which one gives me the lowest. Now, what about the red numbering system? If I go with the red number system, I'll have 2 metals on carbon number 2, and then I have the ethyl on carbon number 4. If I sum up, I'm getting an 8. So the red numbering gives me the least location, the least sum of the location of the substituents on the chain. So this is the correct one, because the rule says that you have to number the chain from the end that gives the substituents the lowest number. Okay, whether there's one or more substituent. If there is one or more substituent, number the chain from the end that gives it the lowest number, that gives it or them the lowest number. Okay, then if there are multiple groups, like here we have 2 metals, so we'll say dimethyl in the name. So in fact, if I'm to name this, first I will identify the longest chain, 6 carbons, so 6 is hex, there's no pi bond, xn, and then I have 2 metals, so I should give that part the name dimethyl, and this is an ethyl. Now you have to write the name by following the alphabetical order. So you first start by listing the substituents, then the longest chain name. E comes before M. You don't consider D, because D is just referring to the multiplicity, how many times you see the same group appearing in the longest chain. So you compare E and M. E comes before M, so we'll list E first, and the ethyl is on the 4th carbon, so 4-ethyl. We use hyphens to separate numbers and alphabets. Okay, and then another hyphen. Remember, we are going with the red numbering system. The blue one failed because it gave us a high sum of the location of substituents. The rule is the substituents must have the least position on the chain according to your numbering system, either from the left or right. So you have 2 metals, so it's dimethyl, but those 2 metals are on the 2nd carbon, so you write 2, 2, because they are separate. You write twice. And then dimethyl, because there are 2 metals, and then hexane. So the official IUPAC name, International Union of Physical and Applied Chemistry, the IUPAC name for this molecule, which happens to be this molecule, okay, that's your ethyl, and these are your metals, just the same thing. The IUPAC name will be 4-ethyl 2,2-dimethyl hexane. Let's do more examples. So again, to emphasize, in red, you have to identify the longest parent chain, identify the substituents connected to the parent chain, assign the location of each substituent, making sure that you give the substituents the lowest locant position possible. Then you name the compound starting with the substituents, which are preceded by their number, position, or location. Substituents are listed in alphabetical order. Hyphens are used to separate numbers and letters. Okay, so this slide is very important. So let's try naming this one. So again, I've drawn the structure twice so that we can number from left or right. If you number from the right, this will be the longest chain. If you number from the left in blue, that will be the longest chain. Now next, you can use a trick to determine which is the correct numbering. Remember, the location, the locant position, the location of the substituents must sum up to the least number for you to choose that system of numbering. So in this case, I have metals. These are CH3s. I hope you know that. Each end is a carbon. So the CH3s are on carbon 3, and of course there's another one here on carbon 5. So you can take this numbering in red system and sum it up, you get 11. Do the same for the blue. You'll have the 2 metal groups on the 4th carbon. you write the 4 twice, and then you have a 2. You sum it up, you get 10. So which is the correct numbering? This is going to be the correct numbering because the substituents position sum up to a lesser number. So this is wrong. 10 is less than 11, you go with 10. So the name should be, first list the position of the substituents, which is 2, 4, 4, and then hyphen, because it's a numerical separated from an alphabetical. You have 3 metals, okay? You have 3 metals, so it's tri, methyl, identity of the substituent, and then you have 6 carbons in the longest chain, so hexane. So you don't want to use these numbers, because that would be the wrong one. You have to prioritize the substituents, make sure the substituents are summing, the position of the substituent is summing up to a lesser number. So the second numbering is correct. Use the same application. So number from the left, right, the longest chain will be 6 carbons. Okay. And then sum up the substituents. So location, the locant position, you have 2, 4, and 5. In red, you get 11. Here you have 2, 3, and 5. Same molecule numbering from the right. Gives you 10. So the second numbering, the blue numbering, is correct, which gives us the correct name. So again, you have a metal, you have a metal, you have a methyl. So it's trimethyl, and they are on the second, third, and fifth carbon. So it's 2, 3, 5 hyphen trimethyl hexane, because there's 6 carbons in the longest chain. Okay. Okay, we'll continue from there.